Hello and welcome to STEM Education. I am Syed Wahaj and today we are going to learn physics for the 11th year of this course. So the topic that we are going to deal with today is magnetism. Magnetism. Okay. That is something that we are going to deal with today. Okay. So what this course is all about? What is a magnet? That is the question. That is something that we are going to learn today. Okay. So there was a place in Turkey. In Turkey, there was a place. The name of the place was Magnesia. Magnesia. And in Magnesia, there were stones which were known as lodestones. Lodestone. And this lodestone has a characteristic of attracting. It had the characteristic of attracting few metals like iron, nickel, and cobalt. Okay, so we had in Turkey this place known as, there were stones present in that area, and those stones were known as lodestones, and they used to attract few metals like iron, nickel, and cobalt. Okay, so they used to attract few metals, few metals, few metals like iron, nickel, and cobalt. Okay, since these stones were found in Magnesia, they later came to be known as magnets. They later came to be known as magnets. So if a layman would ask me this question, that what is a magnet, I would say that magnet is a kind of stone or something or a material that attracts naturally metals like iron, nickel, and cobalt. Okay. Now the question arises, what is the characteristic of these stones? What is the characteristic of this lodestone? What is the characteristic of this lodestone? How does it behave? And what kind of influence does it exert on the surrounding in which it is kept? And how do they interact with each other? Okay. So what we did, we took a bar-shaped lodestone. What we did, we took a bar-shaped lodestone. So we had lodestones, and the lodestone was made up of something that used to attract iron, nickel, and cobalt. Okay, and when we tried to cut that lodestone in the shape of a bar, and we tried to keep it free of any other influence at any place on earth, then it automatically arranges itself in the north-south direction. Okay, so let's take a table here. Let's take a table here. This is a table. Okay, let's make a table here. Okay. There we have a table. Okay, a nice and tidy table. So here we have a table. Okay. And so this is one leg of a table. This is another leg of the table. This is another leg of the table, and this one is again another. Okay. So what are we having here? We are having a table, nice and tidy, a table, a green table, and this table has a special characteristic that the surface of the table is very smooth. It is very smooth, very, or rather we say extremely smooth. It is extremely smooth, extremely smooth. What does it mean? What do we mean to say that what do we mean when we say that it is extremely smooth? It means that if we are going to put something, if we are trying to put something on this table, and this table is trying to, this table won't stop the motion of that particular thing which is kept on the table. Okay. So, Siam, can you listen? Is my voice audible to you? Is my voice audible to you, Siam? Okay, great. So today we are actually studying, today we are studying about magnets, magnetism. Basically, we are trying to study about magnetism. And first thing that we concerned ourselves with was where does the term magnet come from? So there was a place in Turkey, and the name of the place was Magnesia. And in this Magnesia, there was some stones found naturally, and these stones had a special characteristic that they used to attract iron, nickel, and cobalt. These were some of the metals that they naturally and automatically they used to attract. So, on the basis of the name of place Magnesia, we started calling these magnets, these lodestones, as magnets based on the name Magnesia. Okay. Now, we further tried to investigate what are the special characteristics of these lodestones or magnets, if if we call it like that. So what we did was that we took a bar-shaped lodestone, okay, a bar-shaped lodestone, and that bar-shaped lodestone was known as a bar magnet, a bar magnet. Okay. So what is a bar magnet? A bar magnet is something which is shaped in the form of a bar, and after that we made a table, a very extremely smooth table. The surface of this table is extremely smooth, and on this surface, if we are going to keep anything, it can slide very easily. It is not going to cause any hindrance when something tries to slide over it. And we have kept this table in such a manner that towards this end, if somebody goes towards this end, they will reach to the north pole of Earth. North pole of Earth. And this one goes towards the south pole of Earth. South pole of Earth. So this would be the east, this would be the west direction, and this is going to be the east direction. East direction. So this table is kept like that, so that one edge of this table is towards the North Pole, another one is towards the South Pole, the other two would be, one of those would be towards east and other would be towards the west. That's the kind of table we are having with. So what we do now, we use this bar and we keep this bar of magnet or lodestone like this. And after keeping it like this, we did a paint job. We painted this end of the bar magnet with a red. Half of this bar magnet was painted red. This one was painted red. Good. Okay. So we have this bar magnet. One end of it is painted red, and the other end of the bar magnet is painted yellow. Let's say we painted yellow. Okay. This is the bar magnet that we have. Okay. So this is a bar magnet. One end of this bar magnet is painted red, another one end of this bar magnet is painted yellow, and this bar magnet is kept on a table. This table is very smooth. Why smooth? Because if somehow this bar magnet tries to slide over this table will not stop this bar magnet from sliding. Okay. And what we did, when we kept it like that, it automatically arranged itself in this direction. Okay. So it was arranged in this direction. So let's do one more thing. We take it like that, and we kept it like this and left it. Then automatically it again arranged itself like that. Okay. So what we experienced, what we observed while doing this experiment, a little bit of experiment is that whenever this bar magnet was free to arrange itself in whichever direction it pleases, it always arranged itself in the north-south direction. It always did like that. And nobody knew, nobody understood why it happened like this, but they did understand that somehow there was some kind of influence because of which it always got itself aligned in the north-south direction when there was no hindrance from outside, when it was free to arrange itself in whichever direction it pleases. So that's what happened with this magnet. Whenever it wanted to arrange itself, it always arranged itself in the north-south direction. Got it? So this red one, this red portion of this bar magnet later came to be known as north-seeking pole. It later came to be known as north pole of bar magnet, or magnetic north pole, magnetic north pole, magnetic north pole, or north seeking pole, north seeking pole, right? That is the name of this end of this bar magnet. And the one towards the other end that always used to face towards the south direction of the earth, it came to be known as magnetic south pole, magnetic south pole, or south seeking pole of the magnet. Now we understood one thing about this bar magnet, that whenever we had a bar magnet, we always had two ends of that bar magnet, and one of those ends would always try to align itself towards the north direction of Earth, and another end of that bar magnet would always try to align itself towards the south end of the magnet, the south pole of the Earth. So the one always facing towards the north got to be known as the north pole of the magnet, or the magnetic north pole, and the one always facing towards the south came to be known as the magnetic south pole, or south seeking pole of the magnet. So that's what we have understood. Got it? Okay. Now we took two of these bar magnets. One, and let's take another one of these, two of these bar magnets. Now that is how they align themselves whenever they were free to move in the influence, under the influence of Earth. But what happened when we brought two of these closer together. So now what we are having? We are having two bar magnets. So this is one bar magnet and this is the other bar magnet. So let's do one thing. Let's arrange it like this. Let's arrange it like this. And let's bring them together. So what is happening here? The North Pole, the red one is the North Pole, the red one is the North Pole, magnetic North Pole, and the yellow one is the magnetic South. Okay, this is South Pole, and this is the magnetic North. Right? What's going to happen here? What will it happen? Here we can see that the North magnetic pole is facing the South magnetic pole, and what would happen? They would attract each other. The North Pole would be attracted towards the South Pole. Okay, so the North-seeking pole or the North magnetic pole would be attracted towards the South-seeking pole. Okay, let's make another thing. Let's have it here, and let's turn it again. This. So let's turn it like this. Then here we have this North Pole and again this South Pole. What would happen? They would repel each other. They would start repelling each other. They don't like each other. The North Pole doesn't like the North Pole. The South Pole wouldn't like the South Pole as well. The South Pole wouldn't like the South Pole as well. So let's rotate it like this. And, so what we can say, the North Pole would repel North Pole. They don't like each other. The South Pole would repel South Pole. They won't like each other. So we can say that like poles do not like each other, or like poles repel each other. Like poles repel each other. Repel each other. And here we can say that unlike poles would attract each other. Unlike poles would attract each other. Okay. So the like poles would attract each other. So the unlike poles would attract each other. North Pole would attract North Pole, South Pole. North Pole would repel each other, and South Pole would repel the South. So it is something like charged particles. Do we remember that if we have a positive Q charge and then we have another positive Q charge, these are two charges, they would repel each other. And if we have a negative Q charge and another negative Q charge, they would also repel each other. But if we have a positive Q charge and then we have a negative Q charge, they would attract each other. Okay. So it is just like that. So let's say it is, let's make it. It's something like that. It's something like this. It's like that. Okay. So what we do, we assume that this North Pole behaves like a positive charge and this South Pole would behave like a negative charge. Okay. Like a positive charge and negative charge would attract each other, the North Pole and South Pole would also attract each other. Like the North Pole and North Pole would repel each other, similarly, like North Pole would repel another North. So what we do sometimes, we assume that there is something like a magnetic charge. We assume, we think in our brain. We don't really have an experimental reality a real thing, something like a magnetic charge, but we assume that North Pole and South Pole behaves like positive and negative charges. We sometimes assume that a North Pole contains something like a positive magnetic charge. We can assume, we can imagine, we can imagine, we can imagine or assume that North Pole acts as a positive charge, a positive magnetic charge, positive magnetic charge. We can imagine that North Pole acts as a positive magnetic charge and South Pole acts as a negative magnetic charge. Magnetic charge. Okay. The only difference here, so you can go ahead and write that down, all these things, so that it remains clear in your mind. And one thing before writing that, we have to write one thing over here as well, that whenever, let's write it down here somewhere adjacent to it. Let's write down adjacent to it. Let's write it down here, that we can observe that whenever we release a power magnet in such a way that it has the freedom to align itself, along any direction of its choice. Okay, it will always align itself along the north-south direction. It will always align itself along the north-south direction. And the end facing north is known as magnetic North Pole. And the one facing south is known as magnetic south. Okay, so that is something that we should write down. I would give you a little bit of time to copy it. Okay, to copy it and write that down for your further references. So write it down. Go ahead. take a note, take a snapshot. You can take a snapshot of it as well and write down in your notebook. Write down in your notebook. Go ahead, write it down. Okay, I think we are done with it. Should I continue? Give me an indication. Should I continue? Okay. So let's move on. So the thing with positive and negative charges, electric charges. So electric charges, we can find an isolated positive or negative charge, positive or negative charge. Okay. So if there is a positive charge, we can have a positive charge while there is no negative charge in the surrounding of it. Like we can have a plus Q charge over here. We can have a plus Q charge over here. So we have a plus Q charge here. Okay, you're saying something? I couldn't see. Okay, yeah, sure, I can do that. Sure, you can have it. We can post that meeting, and the YouTube link for the same would be provided to you later on. Okay. So you can also go ahead and write all those things down from the YouTube as well. So let's pay a little bit of attention towards the electric charges. We know that there are electric charges like electrons and protons in atoms. So if we are having a proton somewhere, let's write it down that here we are having a proton, a plus P, a proton, without the presence of any electron in the surrounding. So we have a positive charge here, and in the vicinity of this positive charge, we have no negative charge, which means we have an isolated positive charge. Also, we can have an isolated negative charge like that of an electron, like that of an electron. Okay. So we can have an isolated proton, we can have an isolated proton. Also, we can have an isolated electron. We can have an isolated electron. Okay, both of these are possible. Isolated electron. So there is a possibility of finding an isolated positive charge and an isolated negative charge. This is a possibility. So if we are having a positive charge somewhere, and in the vicinity of it, there's somewhere a negative charge, we can draw arrows from positive to the negative charge. Draw positive to the negative charge. It's like, it goes like this. Okay? It goes like this. Okay? So there are lines coming out of these positive charges, and these lines are entering into the negative charges. Okay? So these lines are known as the electric field lines. These lines are known as electric field lines. And these electric field lines have certain properties. These electric field lines have certain properties. First property is they emerge from the positive charge, and the second property is that they terminate at the negative charge. And the third thing is that these lines, these electric field lines, do not cross each other. Why? Because they show direction of electric influence at any point. Okay. So we try to understand all these things that we've written here. What we have tried to say that when we are actually discussing about electric charges, we have two types of electric charge. A positive charge. Electric charges are of two types. There is a positive charge and then there is a negative charge. When we are talking about electric charges, we can find a proton sitting somewhere, and an electron sitting somewhere without having any positive charge. An electron can be present at a location without having any positive charge adjacent to it. Similarly, we can have a proton, a positive charge, sitting somewhere without having any negative charge in its surroundings, which means there's a possibility of finding an isolated proton or an isolated positive charge, and also we have a possibility of finding an isolated negative charge, that is an isolated electron. There's a possibility of finding out that. Also, if we are having some positive charge adjacent to a negative charge, we would see that some lines would emerge from the positive charge and they would end up at the negative charge. These lines which are emerging from the positive charge and which are entering to the negative charge, these lines are known as electric field lines. And these electric field lines have certain properties. The property is that they emerge from the positive charge and they terminate at the negative charge. And there's a third property as well, which I'll tell you, that at any point on this line, if there's this point that we are talking about, let's say that we are concerned about this point A, and somebody asks me that what is the direction of electric influence at point A, we would draw a tangent on this, a tangential arrow on this white curve, on this electric field line. A tangent to this electric field line at point A would give the electric influence or electric field intensity at point A. Also, if we have chosen another point for ourselves, let's say we have chosen this point for ourselves, and let's call this point as B, and someone asks me what is the electric influence or electric field intensity at point B, we would draw a tangent at this curve on point B. So this green arrow would be known as EB, or electric field intensity at point B. It gives the direction of electric influence at point B. So in other words, the electric field lines basically try to tell us the direction of electric influence at a point. Okay, so that is why when we are trying to draw different electric lines, and somebody comes along and he draws two electric lines like this and another electric line like this. So he comes along and he says that these are two electric field lines at a point. What he means to say is that at the point of intersection, A, if someone asks me what is the direction of electric field intensity at point A, it would get very difficult for me to tell the direction, because I would either have to draw a tangent to the green line or I would have to draw a tangent to the yellow line. But I will not really be able to decide where exactly should I draw this tangent to. This arrow should be tangential to the green line, or whether this arrow should be a tangential to the yellow line. That is why it would cause a lot of difficulty and confusion regarding our understanding about direction of electric field intensity at point A. That is why having electric field lines crossing each other is something not advisable. That is why whenever we draw electric field lines, these electric field lines do not cross each other. They cannot cross each other. Because if they are going to cross each other, they would be showing two different directions at the same point, two different directions for the electric field intensity. And one electric field intensity can't have two directions. Like one force can have either that direction or this direction, but it cannot have two directions simultaneously. So electric field intensity can't really have two directions simultaneously, right? So that is why the electric field lines do not cross each other, because if they would be doing so, it would cause a great difficulty. It would cause a great problem for us, because then we won't be able to really understand what exactly is the direction of electric field intensity at the point where they are going to cross each other, right? Got it. Okay. So this is the whole discussion. The whole discussion is about the electric field lines, electric field intensity, electric charges. But the chapter that we are presently dealing is the electric field. It's not about electricity. It is about magnetism. But as we have earlier seen, that the positive charge and the negative charge are similar to that of the North Pole and the South Pole. So instead of North Pole, we can take a positive magnetic charge, and instead of the South Pole, we can take a negative magnetic charge. So that is why we are having a discussion about electric charges and electric field lines, After that, we will similarly deal with the magnetic fields and magnetic field lines. So if you want to write it down, go ahead and write it down. I will give you some time, take some time and write these things down so that I'll go ahead. I'll move ahead with it. Okay, well, write it down. Good. Now, these electric field lines, these are important things, and also write down these properties. These are important things. These properties of electric field lines, this is important. Okay, I think you've written down. Now let's study the same thing about the magnetic field and magnetic field lines, how they behave. Okay. Now about north and south pole. North and south magnetic pole. South magnetic poles. Okay. So the north pole stands for the positive charge and the south pole stands for the negative charge. Like the positive charge is a north pole and the negative charge is a south. So we do not have the capacity to find out an isolated north or south pole. See? We do not have, we do not have a negative, an isolated north or an isolated south. An isolated south. Okay. What does this mean? What exactly does this mean? That we cannot have an isolated north or an isolated south pole. Let me tell you what does it mean. Hold on first. Let me copy it down. Okay. So we have this bar magnet. It has this north pole and this south pole. It is made up of two poles. So if somebody wants to have a north pole just to himself and it doesn't like south pole, let's try and do one thing. Let's try to break it apart from this middle portion. Okay. So this middle portion, we think that we can break it down like this, like having an individual north pole here and having an individual south. That's what we would be assuming, that here this end is called north pole and this end is called south pole. So let's break it down from the middle. We'll have a north pole and a south pole. But that is not possible, because once we try to do that, what would happen? It would automatically get converted. It would automatically get converted, this half portion of this This one, this half portion would get converted into south. And this half portion of it would get converted into north. This would start behaving as a north. Okay. Okay. So we try to break it into two parts. We tried to have a separate north pole and a separate south pole, but this did not happen. It automatically got converted into another north-south pole and another north pole. This became one bar magnet and this became another bar. It automatically happened like that. We can't really have a north pole without its own south pole. That's not a possibility. So that is why we have written down over here that we do not have an isolated north or an isolated south pole. That is an impossibility. If somehow somebody somewhere finds out an isolated north pole or an isolated south pole, he would be immediately awarded with the highest prize in science, that's called the Nobel Prize. He would be awarded Nobel Prize immediately within 2 hours. Somebody would be coming along from Europe and he would be giving this Nobel Prize to that person. Oh my God, you have brought us an isolated north or south pole. That's impossible. That doesn't happen. That can't possibly happen. You can't have a single north pole without having a south pole just adjacent to it, just touching it. Okay, that's an impossibility. So this is something that we have to understand. This is a basic difference between electric charges and the north and south magnetic pole. Though the north magnetic pole behaves like a positive charge, the south magnetic pole behaves like a negative charge, but a positive charge and a negative charge can exist alone. Like a single proton can exist, a single electron can exist without having any proton adjacent to it. A proton can be there without having an electron adjacent to it. There's a possibility. An isolated proton is possible, an isolated electron is possible, but an isolated north pole is impossible. We can't really have an isolated north pole or an isolated south pole. And if we try to break down a bar magnet in two pieces so that we can have a different north pole to ourselves and south pole to ourselves, it doesn't happen, it doesn't work. It automatically, the north side automatically gets converted into a smaller north and a smaller south, and the south would automatically get converted into a smaller north and smaller south itself. So we can say that an individual north pole or individual south pole, an isolated north or isolated south pole is an impossibility. It does not happen. And if somehow, somewhere, somebody proves that it can exist, it will completely change our understanding of the science as we understand it now, because a lot of laws based on which things operate around, like fundamental laws of physics, like Maxwell's equation, these kind of things are basically dependent upon this understanding that north and south pole cannot exist alone. So that is the basis of fundamental physical laws. So if somehow somebody finds out an north pole which is isolated, then it would completely shatter our understanding of the science, and it would cause a big furor and a big trouble in the scientific world. So this is something that you have to understand. So it's a big thing to be understood while understanding about the magnetism. Okay. Then again, we have like a north pole and a south pole that makes up like a positive charge and a negative charge. A combination of a positive and negative charge makes up a magnetic, an electric dipole. So if we have a plus Q charge over here and a minus Q charge over here, this is a combination of positive Q charge and a negative Q charge, and this whole thing constitutes an electric dipole. This is known as electric dipole. Okay, So what is an electric dipole? An electric dipole is a combination of a positive charge and an equal negative charge kept at certain distance r from each other. So we have two charges, a positive charge and a negative charge. Both of them are kept at a distance r from each other. They constitute an electric dipole. Okay. Similarly, a magnetic north pole and a magnetic south pole together, they constitute a magnetic dipole. So a bar magnet can also be referred to as a magnetic dipole. It is called a magnetic dipole. A magnetic dipole. Why? Because there are two poles. One is north pole, one is south pole. That is why a dipole. Di means two. Dipole means two poles. So why do we call it a dipole? Because there are two poles. One is the north pole and another is the south pole. Okay. So a bar magnet can also be referred to as a magnetic dipole. Okay. And like electric field comes out of positive charge and goes into the negative charge, similarly, magnetic field lines come out of the magnetic north pole and enters into the magnetic south pole. Okay, so if we have this magnetic dipole, we can draw magnetic field lines like we have drawn magnetic electric field lines for the electric charges. So what happens? Magnetic field lines come out of the north pole, it goes like that and it enters into the south pole. Okay. So what is this? Okay. So what are these? So this is like a positive charge and this is like a negative charge. So magnetic field lines, here we are talking about magnetic poles. So the magnetic pole field lines are coming out of the north pole and they are making a circular shape, not exactly circular, but a curved shape, and then they enters into the south pole. But what happens inside the magnet? That is an interesting thing, that it completes the loop. It completes this loop. It just completes this loop, right? Okay. So inside the magnetic field also runs inside the magnet, right? So outside of it, it goes from north to south, but inside of it, it goes from south to north. Okay. So when we are talking about magnetic field lines, we have to understand few things. When we are talking about magnetic field lines, we say that magnetic field lines emerge from north pole. Magnetic field lines, let's write it down, and enter into the south pole. Magnetic pole. But they do not terminate at the south pole. Right? So earlier when we were talking about the electric field lines, we knew that field lines emerged from the positive charge and they terminated at the negative charge. But here they emerge from the north pole and they enter into the south pole, but at the south pole they do not terminate. Important point. They do not terminate. they make a complete loop inside the magnet. Rather, they make a complete loop inside the magnet. Rather, they make a complete loop. A complete loop inside the magnet. Complete loop inside the magnet. Going from South Pole, to the North Pole inside the magnet. From South Pole to North Pole inside the magnet. Got it? So inside the magnet, they go from North Pole to the South Pole. So let's make a bar magnet like this. This is the North Pole. Let's color it down like this. Okay, we should have chosen take up pen, right? Let's complete it. Complete it. Okay. And then we have so what happens? This is a magnetic field line which is coming out of the North Pole. It goes all the way round and round and round, and it enters. It goes round and round and round, and it enters the South Pole. So what it happens? It does not terminate. It does not dies at the South Pole. It goes inside from the south to north within the magnet. It goes like this. So it makes a complete loop. So that is the difference between an electric field line and a magnetic field line. An electric field line goes from the positive charge to the negative charge, and it dies at the negative charge. It does not continue from there. But about a magnetic field, it emerges from the North Pole, it goes into the South Pole, and goes complete and makes a complete loop inside of it. Okay, so that's what it's all about. So that is the idea of a magnetic field going along like this. So that is one thing. Another thing is that magnetic field lines also do not cross each other. Magnetic field lines do not cross each other. Why? Because magnetic field lines also tell us about the direction of magnetic influence at a point. So magnetic field lines do not cross each other. That's another point. The second point is magnetic field lines also do not cross each other. Do not cross each other. Okay. So if we have a magnetic field line, it goes from a positive charge, it makes a complete loop. They do not cross each other. So if there are two magnetic field lines, this is one magnetic field line, and we have to draw another magnetic field line like this, it is not permissible. We cannot have two magnetic field lines crossing each other. Why so? Because at the point of the intersection, we would be having two different directions to the magnetic field, which is definitely not possible. So if two magnetic field lines are crossing each other at a certain point, it would mean that at the point of the intersection, the magnetic field is having two different directions, which is an impossibility. So we have magnetic field lines and they do not cross each other. Okay? Okay. So I think you should go ahead and write this down as well, magnetic field lines, about how they operate. This is a very important thing. Go ahead and write it down. Okay. Okay. Got it? Okay. So now we have understood about the magnetic field lines and the idea about how magnetic field lines are there. Now let's talk a little bit about the magnetic materials. About magnetic materials. Magnetic materials. Okay. So what are magnetic materials? Magnetic materials are those materials which show magnetic behavior. Something which can attract nickel, cobalt, iron, such kind of material which produces magnetic field line, which can be used to make a bar magnet like diaminium. Diaminium magnets. Okay, we have magnets in our earphones, in our speakers. Okay, so we have diaminium magnets. Diaminium magnets. So they are very strong magnets, and they do not lose their magnetic properties easily. These are known as magnetic materials. So what are magnetic materials? Magnetic materials are those materials which can be used magnets simply. Materials that show magnetic behavior. Magnetic behavior. Materials that show magnetic behavior are known as magnetic materials. Magnetic materials. Okay. Okay. So we have soft magnets as well as hard magnets. So when a magnetic material is there, so we have a soft magnet, and then we have a hard magnet. Hard magnet. Okay. So what is a soft magnet? A soft magnet is something which is like easy to touch and it's soft to touch. No, it's not like that. It's not about the quality of material. Like it's not the hardness of material that we're talking about here. When we are talking about soft magnet, it doesn't mean a soft material. When we are talking about hard magnet, it doesn't mean we are talking about a hard material. It matters. It means that how much magnetic property it can achieve. Okay. So soft magnet is that kind of magnet which achieves magnetic properties easily. A soft magnet is that magnet, that material, which easily gains magnetic property and also it loses magnetic properties easily. Okay, something which can be made magnet easily, is known as a soft magnetic material, and it can be so like soft iron core. We have soft iron core. So there is something which is known as transformer, and these transformers are used to distribute electricity in your area. You might have seen these transformers from where you get supply at your home. So in these transformers, we take some material like soft iron core, and we wind wires over these iron cores, and they get easily magnetized and easily demagnetized. So these materials, soft iron core, these kind of materials, they get magnetized very easily. So if we have a lodestone with us and we take a soft iron nail and we roll this nail over this lodestone, this process would easily make the nails get magnetized, become magnet itself. So we have a nail made up of iron, soft iron, and then we have a lodestone. This iron nail, like we have this lodestone, this is called lodestone, magnetic lodestone, and then we have okay, like this is a nail. Okay, this is a nail. It's made up of soft iron. And it is not magnetic, not magnetized yet. It has not been magnetized yet. So what we do, we take this one and we just rub it on the lodestone. Rub it like 100 times. Let's rub it 100 times. After that, it will become a magnet itself. It will have just, let's say, this will have this north pole and this is south pole. It will become a magnet after it gets rubbed over a lodestone. That is why we call this soft iron as a soft magnet. Why? Because it easily gets magnetized. And similarly, when we are talking about hard magnets, these are the materials. Hard magnets are the materials which do not get magnetized easily. Hard magnets are those materials which do not get magnetized easily. Okay, these materials which do not get magnetized easily, but once they get magnetized, they do not lose magnetization easily. It's hard to get magnetized, and it's hard for them to lose their magnetism. They don't lose magnetism easily, like neodymium magnet. magnets. Okay, neodymium magnets. Okay, so these neodymium magnets, which are used in the earphones, in the uh, in electronic equipments where they produce sound, speakers, and all. These neodymium magnets, they do not leave, they do not uh, mm, magnetism. They do not get demagnetized easily at all. Okay, so this is what it was all about: magnetization and demagnetization. So that is all. So we are going to have the next class, and we will be having this video which we are having in the class. It will be recorded and it will be uploaded to the YouTube, and it will be shared with you shortly after. So if there is any question that you want to ask and there is any confusion which you currently have about the topic that we've discussed today, you can just go ahead and ask me, and I'll try to make that thing understandable to you. I'll try to explain it again. Is there anything that you want me to explain again? Okay. So I think it's all for today. We can have questions in the next class about the different kind of questions that we are going to encounter in the examination. Those kind of questions we'll be dealing with in the next class. Okay. So thank you so much for joining this class today, and we'll meet again in the next class. Okay. Thank you so much.